The first question, very well. As I remember, no student missed this one. Okay, yeah, answer C. So I do not need to explain. Okay, all right. The second one, although you did quite well in general, but I remember 2 or 3 students missed this one. Yeah, answer is 2. Yeah. So here the reason is very simple. The relationship between the JSON inversion and the global inversion. Yeah. So this question is designed to check your familiarity of the nodes. So if you are familiar with the nodes, then it's a simple question. Yeah. But some students, so they didn't study, everything in the nodes, so they may skip something. Yeah. So they answer this question if by logic, yeah, because if you do not have the knowledge, yeah, so we spend a lot of time understand this concept, inversion concept. Then we talk about 2 different types, the JSON inversion or local inversion, the global inversion. So those students, if they do not have that knowledge, they just answer the question by, because that's very common. When you do not have the knowledge, how do you answer the question? So by intuition, your old experience, intuition, or by logic. By logic, yeah. All right. So here, that's the case, okay? Yeah, because if you're by logic, we know global inversion, JSON inversion, quite different. How can you say if an array does not have any other JSON inversion, but based on the logic, there is a possibility it may have the global inversion. Yeah. But actually, because you do not have the knowledge. In the knowledge part, if we look at the knowledge part, we know the JSON inversion can result in global inversion by transitivity property. By the transitivity property, it can result in global inversion. That's the key point. Yeah, but that's the knowledge piece. Okay, so you cannot get this property by logic, by intuition, right? So you have to study it. So this knowledge point, you have to study it. Okay, yeah. So we talk about transitivity property in class. Okay, yeah, because you have one other JSON inversion, another JSON inversion, then these 2 elements also inversion. That's the transitivity. Okay? Yeah. These 2 non-other JSON, but they are inversion. Yeah. Because we can use the transitivity property. Yeah. So here. All right? So here I just use the example. Although most of you know this result, I just explain why those 2 or 3 students missed this question. Yeah. All right. So here, answer 2. Number 3, 1 or 2 students missed this one. Yeah. Overall, it's very good. Yeah. Because it's so simple. First, we know the result, right? Yeah. So we know the formula. Yeah. Some students write a general formula 3n/2, right? Use the floor function, minus 2, the general formula. So you can see, to consider if this algorithm, so we have this algorithm, if this algorithm is in big theta of m, so here I use this chance to check your understanding of big theta notation. So very simple question. But it's easy because we can drop the minor term, right? Minus 2, we can drop the minor term. For the leading term, because floor function is just a plus 1, minus 1 difference, small difference, we can approximate to the non-floor function version, right? And 3/2 constant multiple of n, so that must be in the big theta of n. So that's very simple. All right. Number four, you did quite well. The answer is A. But here, sometimes you may have this case, like you got the right answer, but you couldn't explain why it is the correct answer. Here, this could be the case. I saw one student explain in the right way. So here, possible to arrange, possible or not, when you answer the question, usually you want to find an example that make it happen. Usually, but to make an example that satisfies the given condition, it's not easy. It's not easy. So most students may not get that. So here, let me ask you a question. Can you find an array satisfy the condition? You should have several elements, and make it no element is in place. So all elements are not in place. So one student described the array, the special input, the property. So here, actually, it's pretty simple. So here, let me just draw a diagram. Okay. All right. First, let's assume the right position 1, 2, 3. Okay. N minus 1 n. That's the right position. If this array is sorted in ascending order, then the elements, so they are in the these right positions. Now we want to, do small change to make all elements out of place. The method is very simple. Okay, move element at the position 1 to 2, 2 to 3. So you can call rotation. Okay, 3 to 4, and so on. Okay, and then last element, because rotation, you move it back to position 1. Okay, if you do the change like this, then all the elements are out of place. That's simple. Okay? All right. So making some good examples. And later we have another question. So that's the relatively hard one. You need to do something like this. All right. Number 5. Yeah, number 5. Yeah, actually, you missed the missing rate is much higher. Yeah. The missing rate, I estimate about 1/3. 1/3 of you missed this question. Correct answer is B. Yeah. Correct answer is B. But several students selected D. Several students selected D. Okay. Yeah. So for those select D, I give partial credit. 2 points off. Partial credit. Yeah. Yeah. Because although it's not the best answer, but it is second best. Yeah. All right. So here, to answer this question right, we just use one result we derived in class. Remember, we used the L'Hopital's rule. We derived log function belongs to little, sorry, yeah, I need to write little, very small, little of n to the d, right? This d, we only require d positive. Yeah. D positive. So here in option A, d equals 1,000. Yeah. Option D, d constant equals 1/millionth. 1/millionth. But no matter how small it is, it's positive. Yeah. Yeah. So for those students who select the wrong one, you need to know this result. This result. Okay? Yeah. That's very important. Yeah. All right. Number 6, correct answer, yeah, because increase is faster in the long run. Yeah. Yeah. So you can increase n as much as you want. Yeah. Answer is option A. Yeah. But several students select 2 or 3. Yeah. As I remember, 2 or 3 select B. Yeah. So this one, we need to use another important result we derived in class. So that is the power function n to the d. Yeah. D we require positive. Okay, d belongs to also little o exponential function a to the m with the base a strictly greater than 1. Yeah, that's another important result we derived using the L'Hopital's rule. Yeah. Here you can see, based on that, the base very close to 1, but no problem, it's strictly greater than 1. Okay, strictly greater than 1. Here, the d part, exponent number, it's very large, d, yeah, but it's a positive, and it's fixed. All right, yeah. So those students who select this one, so they use their intuition. Yeah, because the first one, the base so close to 1, although you can do large number of self-multiplications, but based on their intuition, it should increase very slow. Yeah. The second one, n is a very large number, and the exponent number also very large, so they feel the second one should be increasing much faster. Yeah. Yeah. One student, not this semester. Yeah, I have a previous student. One student even use a graphical calculator. Yeah, graphical calculator, some online software. The online software can draw graphs. So that student tried to compare these two functions by drawing graphs. Okay? Drawing graphs, the first one, the curve, the shape of the curve, very flat. Yeah, because, when you draw graphs, the second one increases very fast. Yeah. But the problem is, the graphical calculator, you can only see the graphs for relatively small n, right? If the n is very large, the graphical calculator won't show it. Yeah, you cannot see it. Yeah, so do not use that graphical calculator to tell you which one increases it very fast. Yeah. Because our n can go to infinity, extremely large, and the graphical calculator cannot handle it. Okay? Yeah. All right, so that's this question. Yeah, let me look at the time. I should not go too slow. Yeah. At least before the break, I should finish the first half. Yeah. So then I can, because my second half, I have 10 questions. I counted. I have 10 questions. So the first half, 15 questions. All right. If you have any question, you just type in the chat area, so I can see if I see your question there, I will answer your questions. Okay, yeah. So my second computer, I open the chat area, so I can see your response. Yeah. All right. Number 7, larger. The answer is B. Yeah. A few students. Around three or four, or approximately 3 students got the wrong one. But here I also like, so can you? Yeah, because here our n is a concrete number. Okay, it's not a variable. So here this n, we use n as a constant. Yeah, it's not a variable. Yeah, so it cannot change. We only look at one point. Yeah, so there, if 1 point, then we cannot say the previous result. You cannot use this previous result directly. Yeah, because previous result we look at the n extremely large. Yeah, so it's not a fixed point. So to answer this question correctly, you need to plug in this n number and calculate it. Then do the comparison. That's the right way. Yeah. All right, so here, let me do the calculation. The first one, let's calculate. Yeah. Before the calculation, let me write this 100 to the 10 to the 10th. Right? As 100, we know it's 10 squared. Right? 10 squared to the 10 to the 10th. Okay. Yeah. Then we apply simple algebra property, yeah, because the exponent we can multiply like this. Okay. 2 times 10 to the 10th. Okay. Yeah. So that's n. So this is the, we use 10-based representation, not 100-based representation. Yeah. Then when we take log base 10, that's easy. Log base 10 of n, we only take the exponent part. So 2 times 10 to the 10th. So that's the first number. We put it aside. Next, let's calculate the second one. Yeah. 10 to the 2 times 10 to the 10th, yeah, this whole n number, and exponent, let's write 10 to the negative 6th, 10 to the negative 6th, scientific notation, okay, all right. Then, by that same algebra property, 10 to the 2 times 10 to the 10th times 10 to the negative 6th. Simplification, 10 to the 2 times 10 to the 4th. Okay, all right. Now let's compare these two numbers. This one and that one. And the same base, although there is a coefficient 2. There is a coefficient 2 here. But if you compare the exponent number, one is just a 10, the other 2 times 10 to the 4th. That's 20,000. 20,000, right? Much larger than the first one. Yeah. Much larger. Yes. So you get an idea. How much is that difference? Yeah. Here, the purpose for this question, yeah, you can see we can find some large number such that the power function, although the exponent number is extremely small, but it can beat the log function easily, right? So here the value, okay? You know, comparing with the log function value, the difference is huge. Yeah. So from this concrete example, you can, you know, get a stronger sense in understanding. Yeah. All right, so that's number 7. Yeah, number 8, it's a big one. Yes, finally. Yeah. Before this point, yeah, so for each question, the number of students who missed one relatively small number, okay? Yeah, 3 or 4, at the most 4, yeah, as I remember. I just based on my impression. Yeah. I didn't do statistics, yeah, to save some time, yeah. But my impression, you know, should be good enough. Yeah. Total, we have 19 students this semester, summer, but one student didn't turn in. Yeah. So only 18 students submit. Yeah. So among 18 students, 3 at the most, 3 or 4 students missed one of the questions. Yeah. But number 8, that's a big one. Yeah. So the most students missed, at least partially. Okay. The answer, correct answer is option B. Correct answer is option B, but there are also many students. Some pick A, some pick C, some pick D. Okay? Yeah. Yeah. You know, more than 10, as I remember, more than 10 students select the wrong one. Yeah. Here, let me explain a little bit. Yeah. First, we can see the structure. First, you need to understand the structure. Yeah. From the structure, you can see each term, the x part, you can see it's a power of x cubed function. Yeah. So you can treat x cubed as the base number. Okay? Yeah. So if you want to see better, yeah, although you do not have to, if you want to see better, you can let another variable y equals x cubed. Okay? Yeah. So if you do the substitution, then the p of x, you can write a0 plus a1y plus a2y squared plus a3y cubed plus a4y to the fourth. Okay? And when you see this form, we know the fastest way, because all the coefficients could be arbitrary coefficients. Yeah. So we know by Horner's rule, yeah, so in this case, Horner's rule, we just need 4 multiplications, right? Yeah, 4 multiplication. All right, yeah, 4. Horner's rule. So then, to get a y, you need 2 multiplications, right? 2 multiplication. All right, so total 2 plus 4 equals 6. Yeah. So here you need to, some students, so I noticed some students may not, quickly connect to the Horner's rule. Yeah. Yeah. Some students, because so many students select D. So many students select the D. Yeah, although it's a wrong one, we know it's a wrong one. Yeah. They select D. Why they select D? 8 or more. Yeah. Because yes, you have to. Yes, well, yeah, good question. Yeah. First, we need. Yeah, because here I can hear your sound. Good. So because I changed the microphone. My old microphone remote, I couldn't hear your sound. So now I use a two microphone, so I can hear your sound. Yeah, so your question is yes. We need to do it. We need to multiply all the coefficients, okay? We need to multiply all the coefficients. To answer the student question. Yeah, but the question is, when we, yeah, all right, good, yeah, Elroy, yes, all right. Yeah, now I explain. Yeah, just give me feedback quickly, all right? Yeah, because I feel this question probably very common for many students. Yeah, yeah. So here, let me read the Elroy question in the chat area. Yeah. How is it only 4 multiplications for the first one when the largest one was 3 multiplications and the one with exponent 3 could be 2, right? Yeah, right. Yeah, the answer is that's the power of Horner's rule. Okay? Yeah. How is that? Because we use the power of Horner's rule. All right? Yeah. Yeah. Power of the Horner's rule. The Horner's rule, yeah, why so powerful? Yeah. So for those students who have the similar question as Elroy, you look at the Horner's rule. I think you should still remember Horner's rule. We do factorization, right? A0 plus A1 parenthesis y plus A2 parenthesis y plus A3 parenthesis y plus A4 times y, right? Yeah, that's the trick, or that's the essence of the Horner's rule. When you see this representation, can you see multiplication 1 here, multiplication 2 here? We don't look at the addition, okay? Multiplication 3 here, and last multiplication 4. So you see 4 multiplication. Yeah. So, yeah, because remember we spend a lot of time to derive the Horner's rule, right? So in class, module 1, yeah, we spend a lot of time, yeah. And so after that, then when you see a new question, we should not start from scratch anytime, right? We just apply Horner's rule directly, okay? Because it's so powerful, okay? Yeah. So 4 multiplications, you can do all these things, yeah. All right? Yeah. Later we have a few more questions. We have 2 more questions. We need to apply Horner's rule. Yeah. So, yeah. So make sure you have good understanding of the Horner's rule. Yeah. Here, so you can see its power. Okay. So that's the reason so many students easily select 8 or more. Yeah. Because they forgot Horner's rule. If you remember the Horner's rule, no, you do not need that many multiplications. Okay? All right, yeah. So if you have a question, you can also use your microphone. Yeah, I can hear your sound. Yeah, because I wear another headset. Yeah, I use 2 sets of microphone and speakers. One for recording, one for listening to your response. All right. Number 9. Oh, okay. Question?
So if we are multiplying the coefficient y, we're going to have 4 more multiplications.
Can you explain a little more? Yeah.
So when we multiply a1 with y and a2 with y.
Oh, all right. Yeah. A1 with the whole parenthesis, okay? Not just the y, all right? So there is a big parenthesis after A1. But when you calculate that big parenthesis, you get into it, y1 plus y1 part, you just calculate everything inside that big parenthesis, all right? So y1 plus, you do not need multiplication. When you reach A2, you need another multiplication after A2, but another pair of parentheses. So at A2 place, you need a second multiplication. Right, great. Yeah, inside and out. Yeah. So in your computer implementation, yeah, you calculate from inside out. Yeah, reverse. Yeah, reverse way. So you do not need too many multiplications. Okay. So here, the point is the factorization. Here, in our class, we emphasize the technique of factorization. So here, factorization, or the power of factorization. Okay, the factorization operation, we treat as that some operation. Okay, factorization operation allows you to share multiplication. Okay, share multiplication with or among several terms. Let's say this way: multiplications among several terms. Okay? The old way, you do not share multiplication, right? Yeah. So there are many terms you never share multiplication. But the new way, look at the first, so here, let me show. Look at these 3 terms. They have a common factor y. Can you make, these 4 terms. Covering these 4 terms. These 4 terms, they have a common factor y. Can you make these 4 terms share just the one multiplication on y? Right? Yeah. So you take y out, A1 plus, share. Sorry. Oh, sorry. I wrote the formula I wrote is wrong, right? So that's why that student asked me a question. Yeah, the right one is we factor y out. Okay, y out. Y1 plus A2. Yeah, this is the new way. Yeah, sorry. Yeah, that's why. Yeah, because based on my memory, so my memory got me wrong. Yeah. Oh, A2. Yeah. So let's say another y plus A3, another y plus A4 times y. Okay? Yeah. This way. This way you can see we share multiplications as much as possible. Oh, sorry. Yeah, I think that this is wrong. Okay? Yeah. This is wrong. Yeah. Anyway, we have that correct formula in the notes. Yeah. So here it's hard for me to recover. Yeah. From my memory. Yeah. Y times A2. This should be y. Yeah. Yeah. I got it wrong. Yeah. Oh, so slow. Another y here. Sorry. A3 and yeah, it's too slow. Okay. YA4. Okay. This is the correct structure. Now you can see better. Okay. So we share or we factor common factor y out in this special way, in this nested way. Nested way. Yeah, when you do your project, actually you write the code in this way, right? You write the code in this way. Then you enjoy the result. The result, we just need 4 multiplications. Okay? Yeah. And our Horner's rule is a general result. When we have a degree n polynomial, we just need at the most n multiplications. Yeah. All right. Yeah. We are factoring out. Yes. Right. Inside and out. Yeah. So yeah. Inside out. Yeah. So here for your question, inside out. Yeah. Let me say this way. When we do factorization, we do from outside, then going inside, from outside to inside, that direction. But when we do multiplication, yeah, because when you write your code, you need to implement this algorithm in your program. Then you do multiplication inside and out. Yeah. So that's more accurate way. Yeah. Yeah. Because factorization just restructure the polynomial. Restructure the polynomial. Okay? Change the structure. But you need to implement the multiplication. When you implement it, you do inside and out. Inside out. That way. Okay? Yeah. But the factorization, if you do factorization inside out, then it's hard, right? Yeah. Because when you work from utmost level, then you can cover the maximum number of terms. Then you move inside. So every time you cover as many terms as possible for the factorization. Okay? Yeah. So we call it a greedy algorithm. That's the greedy strategy. Yeah. All right. So yeah, good discussion. Yeah, because so many students miss this one. Yeah. So we are willing to spend a little more time to understand, Horner's rule better. Yeah. So in the midterm, you will have at least 2 Horner's rule questions. Okay, that's a lot. Okay, at least 2 Horner's rule questions. Yeah, 2 or 3. Yeah. Yeah. All right. So let me move to the next one. Number 9, Number 9, I actually explained a little bit in class. Yeah. Yeah. I talk about something in class, number 9. Yeah. Yeah. But still, not too many. Yeah, not too many. Yeah. But 4 or 5 students missed number 9. Yeah. Answer is C. Yeah. 4 or 5 students. Yeah. Those students select A. Yeah. Yeah. Here, let me explain to those 5 students. Yeah. Because so here the linear search. Actually, I talk about this this point a few times in class. Yeah. Because when we write the code, yeah. So here you think about we implement this linear search in a computer program. Okay. Yeah. So in your code, you do not check. So in your code, you do not check if the input array is ordered or not. Okay, you never check it because it is too expensive. The checking is too expensive. Too many comparisons. Think about checking is too expensive. Okay, so we don't do it. We just do the linear search directly. Yeah. And if you do not do the checking, how do you know given array is ordered or not? You never know it, right? If you do not know, you just run your code instruction by instruction. What's the difference between ordered data and unordered data, right? No difference. Yeah. So statement option C, we get same efficiency no matter we process the ordered or unordered array. Because we don't do the checking. If someone tells you it's ordered, you know, so then in your code, you just assume it's ordered, then you can do faster, right? Yeah, but you cannot assume. Yeah. Here you cannot assume because nobody tells you the given data is ordered. Yeah. Here we just the data happens to be ordered. Nobody tells you, but it happens to be ordered. Yeah. But now you have the background of the insertion sort. Yeah. Here I can explain this point better by the insertion sort. Yeah. So here I assume you understand. So look at the insertion sort. Okay. Insertion sort has the property. If the input array is ordered, then it is very fast, right? Yeah. Insertion sort has the property. Yeah. So what's the property? This property. Well, for ordered data, it is fast with big O of n. This fast. This fast. Yeah, we know that's for the sorting problem. This is extremely fast. Okay, for sorting problem. And for the insertion sort, given ordered data, you do not need to tell the algorithm it is ordered. Yeah. Yeah. You just feed ordered data into the algorithm. It is automatically very fast. It is automatically very fast. Okay? Nobody says anything about ordered or not. The algorithm just pick up the ordered property automatically. Okay, so that's the insertion sort. That's the biggest property of the insertion sort. Yeah. But our linear search does not have this property. Okay, the linear search does not pick it up that order the property automatically. Okay, yeah, it is blind, so it cannot see anything. All right, so its internal mechanism does not take advantage of the ordered property. But for the insertion sort, its internal mechanism would pick it up, the ordered property automatically. That's the difference. That's the main difference between these two algorithms. Okay, yeah. Because after you learned insertion sort, you can understand this point much better. Yeah. All right, yeah. So let's move to the next question. Yeah. Answer C. Yeah. I only see 1 or 2 students missed. Yeah, 1 student selected B, option B. Yeah. Sort an array, we know people can use n log n, right? N log n. Yeah. It is not too slow. Okay, it is not too slow. Yeah. But for factorization, yeah, extremely slow. Yeah. So one student even told me it's exponentially slow. Yeah. So actually, it's like that, exponentially slow. Yeah. Although the analysis part is hard, so we don't do the analysis part. You know how to see it is exponentially slow, but the result we have seen, yeah, it's like exponentially slow. Yeah. All right. Yeah. Then number 11, the answer is A. Yeah. Most students got that one. Yeah, because you can see greater than 3, 5, and 4, right? Also greater than 4. So A1 greater than 3 elements, so it cannot be the median. Yeah. But small number, 1 or 2, give me x5. Yeah, yeah, very small number, give me 5. Yeah, x5 less than 1, less than x3, but you cannot say it's less than any other element, right? So it's still possible for x5 to be the median. Yeah. Oh, sorry. Yeah. That's right. Yeah. Because x4, you cannot say which one is larger, which one is smaller between x4 and x5, right? Yeah. Yeah. All right. Number 12. Number 12. Yeah. The answer is 195. But many students give me, so many students give me 196. Yeah. A small number give me 94. Okay? Yeah, but also a few students, give me that 700 something. Yeah, a few. Yeah. Yeah. About 2 or 3. Yeah. Give me, yeah. So here, to calculate that, we use the counting by reference. Counting by reference method. Okay? Yeah. You need to find appropriate reference objects. Appropriate reference objects. Yeah. Because here, it's not easy to keep track of the number of additions or plus signs. Yeah. It's not easy to keep track of it. So we want to use a set of reference objects. Yeah. And those reference objects are much easier to keep track of. Okay? Yeah. So here you can use subscript or superscript, the same. Yeah. Subscript, superscript. So you look at the number, these number 3, 7, 11, 383. The difference is 4, right? Yeah. The difference between two adjacent numbers, 4. So it should be 4k plus remainder, 3. Some students wrote a different formula but equivalent, so it's fine. Some students give me a different representation for the subscripts. So if I see the expression is equivalent to this one, that's correct. Okay, all right. Then this k takes for the first number 0, second number 1, third 2, and so on. Okay, the last one 195. Okay, because you count from 0. So here, if we put a k for each term, okay, 195. But when we associate the plus sign, we associate like this. Each plus sign associated with the following object. The object after it. So then the first one we do not count it. Okay? We do not count it. So that's why there are 195 objects, reference objects, as the answer. But some students they just wrote a formula. So like 783 minus 3 divided by 4. But after they do that, so I think you go the right direction. But those students get lost. They do not know they need to plus 1 or minus 1. Okay? After they wrote the formula, because they know this formula gives a number close to the answer, but maybe plus or minus 1. They are not sure. Okay, they are not sure. This number should be plus 1, minus 1 to make it correct. Some students plus 1, some students minus 1. So then, some give me 196, some give me, 194. But if you use, our understanding, like, counting by reference, so then you know what's the correct number. Okay, what's the correct number? So you won't get lost. All right. Just let you know. Let me look at the time. Yes, I still have a few minutes. But next two questions, I plan to use PowerPoint slides to explain. Because these two questions you missed. Really big. Really big. I would say at least, more than 2/3, even more than 2/3 of you missed these two questions. These two correlated. But you missed in several places. So I will use PowerPoint slides to explain several places that you miss it. So let me move to relatively easier questions. Number 15 is actually relatively easier. The answer is 2. 2 comparisons for the worst case. Worst case, okay? But several students, some students give me 1 comparison. Some students give me 3 comparisons. All right. So first, you need to use this condition. Okay, you need to use this condition. First 3 elements are already in order. Already in order. 1, 2, 3. Okay. X1, X2, X3. Now the fourth one we don't know. The fourth one we don't know. Yeah. But we know we need to do comparisons. Okay. There are, several different ways to do comparisons. Remember the goal, we want to find the second largest element. Yeah. So some students told me, yeah, because here you have 3, x4, you need to compare with each one. Compare it with each one. So then you need 3 comparisons. Yeah. If you want to sort it, you need to compare x4 with each one, for the worst case, right? But here, we do not need to sort it. We just need to find the second largest. We can save the last comparison. We don't need to do the last comparison. After you make the first 2 comparisons, you can already determine which one is the second largest. So you stop. Okay? So that's for those students who gave me 3 comparisons. Yeah. So you can save the last comparison. Yeah. For those students who give me 1, I think it's very likely you consider the best case, right? The best case, you compare it with x3 and you assume it's greater than 3, and the second largest. Yeah. Yeah. But here, worst case. Yeah. Yeah. You need to use the worst case. So you need 1 more comparison to get it. Okay? Yeah. Some students may use another way to do comparison. Then the answer is the same. x1, x2, x3. Some students do comparison with x2. Yeah. x2. Yeah. In this way, you need 2 comparisons. Okay? Yeah. Yeah. For the worst case. Yeah. For the worst case should be x4 greater than x2. Otherwise, less than x2, then it's the best case, not the worst case. Okay? So worst case, you need to assume x4 greater than x2. Then you need another comparison to find the answer. Yeah. That's number 15. Yeah. Number 16, I need to put it in a PowerPoint slide. I need to do a lot of explanation on number 16. Yeah. Number 17, also a lot of explanation. Number 18, a lot. Yeah. So number 20 and 21, yeah, I can explain here. Yeah. These 2. Yeah. Let me use the last 4 or 5 minutes before the break to explain these 2 questions. Then we go to the break. Yeah. After the break, so we move to my PowerPoint slides. Yeah. All right. Number 20. So the problem. Yeah. So the problem. So many students. So although they. Yeah. So because we can apply the trapezoid, finding the area of the trapezoid area. Yeah. The top base 4. The bottom base 1000. Okay? Yeah. And the height. Yeah. So the number of elements. Number of numbers. Okay? Yeah. So we only need to count number of. So then we can write the formula. 1/2 times 4 plus 1000 plus that number. Yeah. So here the difference is 3k plus 1. Right? Yeah. So 3k plus 1. Yeah. Not 4k. 3k plus 1. Yeah. So the first term k equals 1. Second term 2. 3. Yeah. The last one 333. Okay? Yeah, so then 333. Yeah. That's the correct way. Yeah. 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 But many students they just when they wrote this formula, so they did somewhere some mistake. Yeah. And a few other students, they do the summation directly, but a few students, they didn't calculate it. Yeah. They didn't calculate. They wrote the summation formula, but didn't calculate it. So here, you need to calculate it. I need to see if you know how to calculate it. Yeah. The first one. The next question, number 21, then many students miss that one. Some students just do the analogy from the, using from the trapezoid, that formula from the previous one. Okay, yeah, you cannot use the analogy. Okay, yeah, the formula you cannot use the analogy. So the formulas you need to split it based on the structure. Yeah. All right. So 1 square plus 2 square, plus 349 square, right? But you need to multiply several things. Yeah. All the part, even part, right? So 1 square plus, yeah. So you need to do that. In the exercise question set, I give you a similar question like that. Just the number different. Yeah, I changed the number. Yeah. So I give you the calculation way used in that exercise question. Then the solution file I will post. Yeah. So after this class, I will post the solution file. Then you will see the, calculation formula for, for this one. Yeah. Yeah. It takes several steps. Yeah. It takes several steps. But you need to use the right way. Yeah. You need to use the right way to calculate it. Yeah. All right. Yeah. So now it's at the break time, right? Yeah. Let me see. Yeah. All the remaining questions, I put them in the PowerPoint slides. So there are 10 questions. Yeah. So when you come back at 7 o'clock, so then we move to PowerPoint slides. Yeah. All right. Yeah. See you after 7. Yeah. Will the here? Yeah. Let me look at. Will the solution file have the work to solve? Yeah, have the work. Yeah, Julia. I give the, even, yeah. So I wrote the work. Yeah, I wrote the computation details. Yeah, explanation. Yeah, and another question. Why did we ignore x1 again? Yeah, x1. Oh yeah, that question, right? X1 could you repeat? Oh yeah, I remember. Yeah, you talk about the reason is we just find the second largest, right? Yeah, so we ignore x1. X1 too low. When we reach x1, we got the second largest, right? When we reach x1, we already got the second largest. So we do not need to do anything when we reach x1. Okay. Yeah. All right. Yeah. Think about that. Yeah. All right. So let's take a break.